All right, you guys, the last category of related rates problems that we're going to talk about deal with angular measurement. These are actually going to feel, I think, pretty similar to the work that we do with the Pythagorean theorem problems. It's just that we need to rely on our trig functions for these kinds of problems instead of the Pythagorean theorem. So let's take a look at example 4. It says, suppose a bird is flying horizontally above your head at 20 feet per second. How fast is the angle of elevation changing when your horizontal distance from the bird is 30 feet? So let's imagine the picture here really quick. We've got a bird. My birds don't look all that different from my airplane. And it's 40 feet above our heads. So we're down here on the ground, and the bird is 40 feet up here. Then it tells us the bird is going at a speed of 20 feet per second. So let's call that dx dt is equal to 20 feet per second. Then it asks, how fast is the angle of elevation changing when your horizontal distance from the bird is 30 feet? So let's keep drawing the sketch here. The bird's going to keep flying past us, so it's at the altitude above our heads, 40 feet, but it's going pretty fast at 20 feet per second. So then it's going to end up over here. Let's give it some feathers and a little beak right there. And it tells us our horizontal distance, so from the ground, this value is going to be 30 feet. So it's asking us, how is our angle of elevation changing? So remember, your angle of elevation is always going to be the measurement from your sight line to where you look up to something. So as a real quick sidebar, our horizontal distance is what we measure our sight off of. And then when you look up from there, that angle measurement, theta, is what we call the angle of elevation. So when we're looking up here, this angle is the theta that we're interested in. So I'm going to draw in another imaginary right triangle right here, because then notice the bird is staying at that constant height, so we can call this value 40 feet too. I'm going to go ahead and erase that 40 feet so it looks a little bit clearer what we're talking about. So ultimately, if we're trying to figure out how fast the angle of elevation is changing, that means we're looking for d theta dt. So we need a way of relating x and theta, and then we can use that equation to solve for how theta changes over time. So this value of 30 feet, our horizontal distance, represents x, and we have dx dt, so how fast the bird is changing, how quickly that horizontal distance is growing. But if we just want an equation that relates x, theta, and 40, we just need to think about what side lengths we have in a right triangle. So relative to theta, we have 40, which is opposite, and we have x, which is adjacent. So when we have opposite and adjacent, that's the TOA part of SOHCAHTOA. So we can say that tangent of theta is equal to, our opposite side is 40 divided by x, which is our adjacent side. So this is our equation that relates theta and x. Now ideally for related rates problems, you want one variable entirely by itself on one side equals another variable entirely by itself. In this case, it's not worth it to try to get theta by itself by taking the inverse tangent, because then you're taking an inverse tangent derivative, which is a lot harder than taking a regular tangent derivative. So at this point, we can just leave this side as tangent of theta. But then to solve for d theta dt, we can take the derivative of both sides. So the derivative of tangent with respect to time is going to be secant squared of theta times d theta dt. And if we want to differentiate 40x, it's probably easier to think about it as 40x to the negative first. So this will become negative 40, and then I'll subtract 1 up here, so it will be x to the negative 2. So I can make this x squared, and then I multiply that by dx dt. So that's going to be my related rates expression. Now, if we think through what we have and what we need to solve for, we're ultimately trying to solve for d theta dt. That's our goal. We have x, that's the value of 30 feet that we're given, and we have dx dt, that's how quickly the bird is moving horizontally away from us. So the one value that we don't have in order to solve for d theta dt is the actual value of theta. But we can definitely get that using our original expression. So in the time where we're interested in the angle changing, the tangent of theta is going to be equal to our opposite side of 40 over our adjacent side of 30. So then we can take the inverse of 40 over 30 in order to get our theta value. So just remember with the work that we're doing here, we always want to be working in radians. Otherwise, the unit values will not cancel out properly. So go ahead and use your calculator to take the inverse tangent of 40 over 30 and see what you get out for your angle measure. So when I plug that into mine for a decimal approximation in radians, I get the value of 0.927. So at this point, then I do have everything that I need to plug in. My recommendation would be, in order to get d theta dt completely by itself, to go ahead and divide both sides by secant squared. And I'll give you one reason why that's a good idea. If I then have d theta dt completely by itself on this side, I've divided by secant squared, but it's hard to plug secant squared into my calculator. However, 1 over secant is the same thing as multiplying by a cosine. So I can instead write this whole thing out as negative 40 over x squared times dx dt, and then instead of divided by secant squared, I can say times cosine squared of theta, which is going to be a whole lot easier to plug into my calculator. At this point, we have everything we need on the right-hand side. So we can say d theta dt is equal to negative 40 over, my x at this instance is 30, so 30 squared. The dx dt is how fast the bird is moving, so 20 feet per second. And then here we're going to have the cosine of our theta is 0.927, and we're going to square that value. So at this point, you just want to grab your calculator and input that entire expression in and see what you get out. So when I plug that into my calculator, I get the value of negative 0.32, and we're working in radians, so we can just say radians per second. So that means our angle is decreasing at a rate of negative 0.32 radians per second, and that should make sense, right? The further the bird gets away from us, the lower that angle of elevation is going to be. So you can imagine it was up here before and then up here, so it is going to be a decreasing value, which is what we would expect. So that's one example of an angular rate of change. Again, not that different from the thought process behind how we would work with our right triangles. It's just that instead of having an x squared, a y squared, and a z squared, we have a length and a height, and then we have our angle value that we're working with.